calculate. So next week we are going to come back to Hardy-Weinburg and we're going to talk more about the information side. Basically, Hardy-Weinburg is an area of genetics that deals with population. So what we're going to do is track changes in frequencies or percents of certain alleles over time in a population. So it's going to tell you how many people in the population are homozygous dominant, how many are heterozygous, how many are homozygous recessive, how many people have the dominant allele, how many people have a recessive allele. And what you can do is compare that. You could compare that information from the 1970s to 2012 and see, has there been a change, and why would a population change the frequencies? What's the reason that it's changing? So part of this is based off an ideal model, and so we're always comparing back to that ideal. This is how we calculate those numbers, and then when we get into evolution, we're going to talk about the 5 factors of Hardy-Weinburg and a little bit more info there. So the first thing that you need to remember is p squared plus 2pq plus q squared equals 1. And on each quiz or exam, I will provide you that equation. And I will also provide to you p plus q equals 1. Now, it might look a little crazy, but we're only dealing with perfect squares and square roots here, so there's only so many options that we can go through. Now, if this is applying to homozygous and heterozygous, we need to identify what these different things tell us. So when we get a percent for q squared, what info does it tell us? So if you look at p and q, which do you think is recessive, p or q? Q. Correct. So q means recessive, and this is going to be the percent of the recessive allele. So essentially, how many people have a lowercase letter in their genotype out of the entire population? If q is recessive, p is then dominant. And this is going to be the percentage of the dominant allele. Now, the only other word that you might hear associated with p and q, I could say, what is the frequency of the dominant allele, or what is the frequency of the recessive allele? So instead of percent, you might also see frequency. So I could say, what's the frequency of the dominant allele? But if I'm asking for p or q by itself, I just want all of the possible little a's and all of the possible capital A's. So this would essentially code out as a little a if we use that as an example, and that would simply be a big A. So far, so good? No one's off the bus? Which would you like to start with, p squared or q squared? Okay, so let's start with p squared. We're dealing with what type of trait? And if it's squared, how many of them do we have? If I have one, so we know this is dominant. Heterozygous dominant is which one? P squared? So this is homozygous dominant. 2pq is then, right, this is heterozygous. This is the easiest one to remember because it has one of each type. So we could say this would be like big A, little a. And q squared would be homozygous so those are the only 5 things that I could ask you to solve for. And how you solve for them is really, really simple. And I don't off the top of my head remember why they chose P's and Q's. That's just what Hardy and Weinberg chose. Just make life more interesting. So, when you solve a question like this, we need to think of, we're just dealing with complete dominance questions. We're not going to get into any that are really complicated here. When I refer to this part of the equation, this is going to reference the dominant trait, and this is going to reference the what? Correct, recessive. So, when I write out a question, listen carefully because this is the toughest part of these problems. When I ask you a question about this, I'm either going to give you the recessive information, because we always start with q squared, or I'm going to give you a percentage that takes into account both of the dominant, and you subtract to get to the recessive. So everything here is going to start with q squared. So let's deal with, let's see, night blindness. Some people have trouble seeing at night. Can't adjust. So night blindness is a recessive trait. And I'm going to say that 81%, let's see, no. Let's say 91% of the population has normal vision. So it's similar to a traditional genetics question where I'm going to give you information about whether the trait is dominant or recessive, but instead of giving you, here's what the parents are, I'm going to give you a percentage that's going to connect back to our information here. Now, 91% of the population has normal vision. So if we were to write the p squared plus 2pq plus q squared equals 1, this part, according to this question, are these people going to be normal or have night blindness? Okay, so these are going to be normal because they're dominant. And if you have this part here, then you would have the night blindness. So all I'm doing in the question here is going back to this information. I said night blindness is a recessive trait. I just rewrote this equation because we have to use it in every single Hardy-Weinberg one. And all I'm saying is that if I know it's a recessive trait, I know that that's what this means. Q squared is about night blindness. The rest of these people here, these percents, are going to be about normal vision people. Okay? Now, I said 91% of the population has normal vision. So is that this number or this number? Right? I said 91% is normal, so I'm going to write 91% here. And often we convert it to a decimal. So if I convert a percent to a decimal, that would be, okay. Even if you feel like you're falling off the bus, try to stay with us here so you can get all the rest of the parts. So 0.91. Now, you can think of it in terms of percents or decimal. I said if I know this, and I know all of this adds up to 1, how can I figure out what q squared is? If this is 1, or if I'm dealing with percents, this would all equal 100. So if 91% is normal, what's the other bit? So if we subtract, we'd find out that q squared is 9%. Now, remember I said everything has to be a perfect square? Is 91 a perfect square? Or could I square root 91 easily? So that's another hint. If I give you something that you can't square root or square easily, I'm telling you you have to subtract to get to the other number. Is 9 a perfect square? Okay, so we can easily deal with 9. So already, gentlemen, we've figured out that q squared equals 9%, which tells us that 9% of the population is homozygous recessive. That's their genotype. Now, everything starts with q squared. So if I convert this to a decimal, right, decimal 0.9 would be 9%, correct? Okay. What I want to do is get to q. If I can get to q, I can solve for p, right? Because p plus q equals 1. So if I square root q squared and I square root decimal 0.9, q will equal 0.3. So 0.09 square rooted will give you 0.3. Now, if we know that p plus q equals 1, I can sub this all in, and I'm sure you can do this the shorter way. So if p plus 0.3 equals 0.1, and I need to subtract 0.3 from each side, then I have p equals 1 minus 0.3, which gives me decimal. Seems to be a lot of giggling. Decimal 7. So p is 0.7. Okay. Now, do I expect you in grade 12 to show me all that work there to get to 0.7? But that's how I figured it out, right? If p plus q equals 1 and q is 0.3, p has to be 0.7 to get to 1. Now, if I have q, I could tell you that the frequency of the recessive allele is what percent? 30%. If I said the frequency of the dominant allele is 70%. So you've already answered 2 more questions. Now, the next thing that the question might ask is, what is the percentage of people who are homozygous dominant? So how do I solve for homozygous dominant? Okay, so if we're dealing with homozygous dominant, we're dealing with p squared. Then it's simply sub in the information that you know. What can we sub in for p? Okay, so I can put 0.7 in. I can square that. That will give me 0.49, which means 49% of the population is homozygous dominant. The last question I could ask is, what is the percentage of the population that is heterozygous for this trait? What do I solve for? 2pq, right? So we write down 2pq, and I sub in, so I go over here and I say 0.7 is p, so 0.7 times q, which is 0.3. And 2 times 7 times 3 will give me 42. So 0.42 or 42%. Now, you can always check to make sure you have these questions right. And I just have to zoom out here for a moment. If we know that p squared plus 2pq plus q squared equals 1, we know that q squared is 9. So if we add 9 plus 2pq, which is 42, plus p squared, which is 49, we equal 100. So if those all end up at 100, you've solved it correctly. If 0.3 and 0.7 equal 1, or 70 and 30 equal 100, you've answered that correctly. So that tells me in a population, 42% of the people are carrying the trait for night blindness. They don't have it, but they could pass that on to their children. If there was a genetic advantage to being heterozygous, we might see that percentage increase over time or decrease over time. But population geneticists are looking at those numbers. Are we all off the bus, or where are we at?